Okay, let's talk about normed vector space. Let's first talk about some properties of vector spaces. So a 2 or 3-dimensional vector with real valued entries, the idea of length is pretty intuitive. You can imagine Cartesian coordinates, um, you can imagine a sphere or a circle, and you can imagine the radius or some vector in 2 or 3 dimensions. And the idea of length is pretty intuitive. Is the distance from 0 to wherever that vector ends. And this idea can easily be extended to any real vector space in n dimensions. So the following properties of vector length become crucial. That the 0 vector has 0 length, and every non-zero vector has positive length. So here the 2 bars around the x represent the length, or sometimes called the norm. So if we now multiply a vector by a positive number, then we change its length without changing its direction. So this positive number is the scalar alpha, and so alpha x, and if you take its norm, is the same thing as taking the absolute value of alpha and the norm of x. The reason we use norm as opposed to absolute value is because x continues to have a direction. So next we basically have that there's a triangle inequality, and that is taking norms as distances. So the distance from point A through B to C is never shorter than going directly from A to C. So because the shortest distance is along the line, and so this can mathematically be written as the norm of x plus y is always less than or equal to the norm of x plus the norm of y for any vectors x and y. So that's the triangle inequality. And so now the generalization of these 3 properties to more abstract vector spaces leads to the notion of a norm, which I just talked about. And a vector space on which a norm is defined is then called a normed vector space. So instead of Cartesian coordinates, now you can think of a vector space. So, and that space, that vector space on which the norm is defined, is called a normed vector space. So normed vector spaces are central to the study of linear algebra and functional analysis. And to write or represent a normed vector space mathematically, we write it as a pair of V and the norm, where V is the vector space, and the this symbol here with the dot representing anything and the 2 bars on either side representing the norm. So a norm vector space is represented as a pair of the vector space and the norm. And a semi-normed vector space is a pair V, P, where V is the vector space and P is the semi-norm on V. So what's a semi-norm? Well, so we are going to talk a little bit more about it, norm versus semi-norm, but we will often omit P or the norm part and just write the V for a space if it's clear from the context what that particular semi-norm or norm we're using is. And in a more general sense, a vector norm can be taken to be any real valued function that satisfies these 3 properties. So the first 2 properties together imply that the norm of x is 0 if and only if x is 0. And a useful variation of the triangle inequality is also around the negative sign, which is the norm of x minus y is always greater than or equal to the absolute value of the norm of x minus the norm of y for any vectors x and y in the normed vector space. And this also shows that a vector norm is a continuous function. So the last thing we'll say here is that the second property depends on a choice of norm, alpha. Remember, that's multiplying by a scalar, alpha, on the field of scalars. And when the scalar field is real, or more generally a subset of the complex numbers, then it's usually taken to be the ordinary absolute value, but other choices are possible. For example, for a vector space over all rationals, one can take the absolute value of the scalar alpha to be the p-adic norm, which gives rise to a different class of normed vector spaces. We'll talk about p-norms in a separate lecture, and hopefully by now you understand the idea behind a normed vector space, and more in other lectures. Thank you from Aditya Mittal from Acme Tutor.